welcome to the final lecture of Engineering 102. In this lecture, we will introduce you to two new features in SOLIDWORKS called simulation and sustainability. Much of the information contained in these slides has been generously provided by SOLIDWORKS. What is SOLIDWORKS simulation? Simulation is a design analysis software package that has been fully integrated into SOLIDWORKS. Simulation simulates the testing of your part's prototype in its working environment. It can help you answer questions such as how safe, efficient, and economical is your design. It's used by students and professionals to be able to evaluate and produce safe, efficient, and economical designs. The traditional design cycle has a number of steps, starting, of course, with the creation of a CAD model, followed by the manufacturing of a prototype and testing. Depending on the results of those tests, an iterative process can then be undertaken to be able to improve the product. By utilizing simulation effectively, the number of design cycles can be greatly reduced. This allows you to virtually test rather than have to manufacture and test the created prototype with each iteration. This reduces not only the number of design cycles, but thereby the cost and the time to market. SOLIDWORKS simulation uses the finite element method. Analysis using the finite element method is called finite element analysis, abbreviated FEA, or otherwise called design analysis. FEA is very general. It can be used to solve simple and complex problems. FEA is well suited for computer implementation and is universally recognized as the preferred method of design analysis for many real-world applications. The finite element method replaces a complex problem by many simple problems. It subdivides the model into many small pieces of simple shapes called elements. At the left, here you see a CAD model of a part with relatively complex geometry. In the middle, you see that this CAD model has been subdivided into small pieces using a process called meshing. In this case, the mesh creates a number of tetrahedral elements. Elements share common points with adjacent elements called nodes. The behavior of an element is well defined by analytical mathematical expressions. SOLIDWORKS writes the equations governing the behavior of each element, taking into consideration its connectivity to the other elements. These equations relate the unknowns, for example in stress analysis, the displacement of each node, to known material properties, external restraints, and external loads. Next, the program assembles the equations into a large set of simultaneous algebraic equations. There could be hundreds of thousands or even millions of these equations, depending on the fineness of the mesh and the size of your model. When local equilibrium is converged by solving these equations of state for every single node, then the large geometry of the overall part has been solved. This bypasses the need to create complex analytical solutions for general problems. In static analysis, the solver finds the displacements in each of the three directions in three-dimensional space x, y, and z at each node. The displacements at each node in each element being known, the program can then calculate what are called strains in those various directions. Strain can be thought of as a normalized displacement. For one-dimensional displacement, the strain can be given by the change in the length, or delta L, divided by the original length, L. Note that strain has no dimension. It is a normalized value. Once the strains have been determined, the program can use mathematical expressions to relate these to stresses. You can think about the stress as a normalized force. More on that in a moment. We'll be performing what is called static analysis in SOLIDWORKS. This is the most common type of analysis. It assumes what's called linear elastic material behavior. It neglects inertial forces. The body returns to its original position once loads have been removed. In static analysis, we calculate displacements and the normalized displacements called strains. Using constitutive relationships, SOLIDWORKS can then calculate the stresses within the body correlated to those strain values, and the internal reaction forces that are represented by those stresses. A material fails when the stress value reaches a certain level. Different materials fail at different stress levels. With static analysis, we can test the failure of many materials. Let's take a moment to define what is stress. When a load is applied to a body, the body tries to absorb the effect by generating internal forces that vary from one point to another. The intensity of these forces is called stress. Stress is force per unit area. You'll note in the equation on the lower right-hand side of the slide, the stress, given by the Greek lowercase letter sigma, is defined as the limit of the ratio of the force divided by an area. As the area goes to 0, this defines what is stress at a point. It's similar to a force, but not exactly the same. Force at a given point is a vector quantity. It has a magnitude and a direction. Stress is what is called a tensor quantity. It's defined by a magnitude and two directions. We can break down the components of stress and think about them as normalized forces. Let's consider a general force given by a vector quantity acting at an arbitrary angle out through a plane called the YZ plane, highlighted on the infinitesimal cube shown in the schematic at the right-hand side. The force can be broken down into a number of components. Those components are the projections of the vector quantity of the force on each of the three axes, in this case the x, the y, and the z axes. These components can be written as F in the x direction, F in the y direction, and F in the z direction. Those components are typically written as subscripts. If we were to utilize our definition of stress and look at the ratio of that force normalized to the area of the YZ plane shown on the infinitesimal cube, and look at the limit as that area goes to 0, we can define three different components of stress. The normal stress, denoted sigma sub x or Sx, is given as the limit of the ratio of the x component of the force acting normal to the plane highlighted in red divided by that area as that area goes to 0. We can also define two other components of stress. Here we can take the y component of the force pointing upwards, the limit of that force component divided by the infinitesimally the area as the area goes to 0 is given as the shear stress that acts in the y direction but exists on the YZ plane. This is written as tau sub xy. Tau indicates that it is a shearing stress, which has a different action as compared to a normal stress. The x component indicates that it exists on the x plane, and the y subscript indicates that it acts in the y direction. Similarly, if we were to take the limit of the z component of the force divided by area and look at the limit as that infinitesimal area goes to 0, we can define the shear stress acting in the z direction on the highlighted plane. So as shown, we can define three stress components related to the three force components that could be described as acting upon this plane. We could similarly derive an additional 6 components as shown on the infinitesimal cube. A total of 3 normal stresses, Sx, SY and SZ, and a total of 6 shear components: tau xy, tau yx, tau xz, tau zx, tau yz, and tau zy. From considerations of static equilibrium, it turns out that only 6 of these components will be independent. In other words, we only need 6 of these components to totally describe the state of stress at a point in a body at static equilibrium. Those are the 3 normal stresses and 3 shear stresses. Positive stress values indicates tension. Negative stress values indicate compression. This is by convention. For special sets of coordinate axes, shear stresses will vanish. These are called principal coordinate systems. So for example, on the right-hand side, you see an image which contains the set of axes x, y, and z, which is an arbitrary set of axes. One might imagine that by rotating the set of axes to a special coordinate system, denoted as 1, 2, and 3, that there will exist only components for stress that are normal to the faces of that infinitesimal cube. In this case, there are no shear stresses. This special set of axes is called the principal coordinate system, and the resultant stresses that only exist that are normal stresses are called the principal stresses. By convention, the largest of those stresses is called P1, followed by P2 and P3. Principal stresses have an interesting use in that we can express otherwise complicated expressions that contain terms for both normal and shear stresses in terms of only the normal components when substituted by the principal stresses in a principal coordinate system. Now that we've noted that stress at a given point within an elastic body is a tensor quantity, we must ask ourselves, if we wish to understand how a material fails, which is normally denoted by a certain threshold strength value, which is a scalar value. It has no components associated with it. There might be associated with that some ambiguity in trying to assign which stress value to compare against a strength. A common way to get around this problem is to utilize what's called a von Mises stress. A von Mises stress is a positive scalar number that has no direction. It describes the stress state at a given point by one number. Many materials do fail when the von Mises stress exceeds a certain level. The von Mises stress can be derived from energy considerations, and you'll learn more about this in future coursework. For now, the following 2 expressions can be utilized to derive the von Mises stress from the stress components. In an arbitrary coordinate system, you can write the von Mises stress in terms of normal and shear stress components, or in the principal coordinate system, you can write the von Mises stress equivalently in terms of the principal stresses. SOLIDWORKS can automatically calculate the von Mises stress for your elastic bodies. In fact, it is a default output for most static analyses. There are a number of steps to performing a simulation in SOLIDWORKS. For a static analysis, that includes the following steps. The 0th step, which is implicit, is that you first create a CAD model. Upon creating a CAD model, you assign materials. You must ask, what is the part made out of? SOLIDWORKS, as you're aware by now, has a built-in database. That built-in database has a number of materials properties associated with each material. For a static analysis, important for that are yield strength, which determines the onset of plastic deformation of a body as opposed to elastic deformation, as well as physical properties such as the density. Once the material has been assigned, we must specify restraints. You must ask what faces are fixed and do not move. We not only can restrain faces, we can also restrain edges or even individual points. and there are different ways in which we can restrain the motion of any given of these entities. Once the restraints have been defined, you can apply your loads. These can be point forces that act in a certain direction at a certain point. They can be pressures or distributed loads that act upon an entire face or line. They can include gravity, friction, heat. There are many kinds of loads. For the purposes of our demonstration and for our last project in this course, you'll be either utilizing a distributed force over a face or a gravity effect as shown in the demonstration in a moment. Next step, which I've interspersed here in between steps 3 and 4, calling it step pi, is to create the mesh. The fineness of the mesh that you might need will determine the accuracy of your results. Once the mesh has been properly defined, you can then run the analysis. Upon successful completion of your analysis, you view the results critically. You can evaluate, for example, what is the factor of safety? What are the resultant displacements or stresses or whatever other numerical outputs you're interested in. There are other kinds of analyses available to you in the simulation package. These include not only linear and nonlinear static analyses, but buckling analysis, frequency analysis, thermal and thermal stress analysis, optimization, dynamic analysis, fatigue analysis, and many more. For the purposes of our coursework, we will be utilizing 3 of these: static analysis, buckling analysis, and an optimization analysis, otherwise called a design study. Let's provide an example of the use of static analysis, in this case to design a telescope mirror. On the right-hand side, you see a diagram, a schematic, that shows a simple telescope mirror. It's a circular disc with a diameter of 2 times A and a thickness T. This telescope mirror is simply supported along the periphery of its bottom edge. A simple support merely means that those points in contact with that support are not allowed to translate in any direction. They are effectively fixed. All other points are allowed to deflect normally. In order to design this telescope mirror, we will need to assign a certain property. In this case, we'll assume that the diameter is fixed at 1 meter and that the material is made from a magnesium alloy. Our goal is to minimize the mass of this mirror by varying the thickness of that mirror, subject to the constraint that the maximum deflection given by delta is less than 1 wavelength of light. We'll assume for the ease of use of this analysis that the wavelength of light is approximately 500 nanometers. The goal of this optimization is to ensure that we are creating a telescope mirror in the most economical fashion. So there are a number of steps that need to be set up in order to perform this optimization study. The first step is to set up your design analyses. These are your simulations. These are the number of steps that were outlined several slides ago, involving the creation of a CAD model, the assigning of a material, the creation of or application of external loads and restraints, the creation of a mesh, and the running of an analysis. In this case, we'll be doing a static analysis. Once you've set up that analysis, you must then create a second kind of study called a design study. In a design study, there are 3 steps. We must define variables, which are those parameters which are allowed to vary, constraints, which are a simple evaluation procedure that SOLIDWORKS utilizes to determine whether or not a given set of variables satisfies your application needs. And finally, goals, which is to say that SOLIDWORKS will try to find the best set of variables that all satisfy your constraints. More on this in a moment. Once this design study has been properly set up, SOLIDWORKS will do most of the heavy lifting for you. When you run the study, SOLIDWORKS will go back to the model, change any variables that you've asked it to change, and rerun the simulation. It will then record the results of that simulation in your design study table, evaluate whether or not the constraints have been met, and then upon running all of the sets of iterations, determine which of those solutions that has met all the constraints optimizes your goal. It is then up to you to critically evaluate the results. Now let's go into SOLIDWORKS and see how this might be implemented. Before creating our first part, let's first enable the SOLIDWORKS simulation add-in by going to add-ins and ensuring that SOLIDWORKS simulation is active. Once you've verified that simulation is active, go ahead and click OK. Let's go ahead and create a part. Before I create my sketch, I'm going to verify that my units are in metric. They're currently millimeters, grams, and seconds. That's perfectly fine. I'll go to Sketch and create a circle on the front plane, centered at the origin. I'll then apply a smart dimension of 1000 millimeters, or 1 meter, to define the diameter. I'll then go over to the Features tab and extrude this sketch to a thickness of approximately, let's call it 300 millimeters. And click OK. We now have a simple model of our telescope mirror. Let's do two things before creating our simulation for our static analysis. First, let's define our type of material by going over to the material, right-clicking, and click on Edit Material. This will cause SOLIDWORKS to bring up its materials database. For the purposes of this demonstration, we'll be selecting a magnesium alloy as the material of choice. Magnesium alloys are very lightweight, yet also very stiff. You'll find magnesium alloys not under steel, but under other alloys. For the purposes of your project, you'll be utilizing gray cast iron, which can be found under iron, and a titanium alloy contained or found within the folder for titanium alloys. You'll be using titanium, 6 aluminum, 4 vanadium. Your version may also say that this is solution treated and aged, and that's perfectly acceptable to use. For this demonstration, let's select our magnesium alloy and click Apply and Close. We can note now that the material is magnesium alloy. Let's also perform one more step before creating our static analysis. In the end, after performing our static analysis, we'll be creating a design study. You've already been exposed to something called a design table. A design table will allow you to change and create multiple configurations of a part by prescribing a series of values for global parameters. Design studies are roughly analogous to that. They do a little bit more for you, but they do go back and change the model according to how you prescribe. And it's often very convenient to make changes to those models using global variables. To refresh your memory, the first step in showing a global variable is to go to Annotations, right-click, and go to Show Feature Dimensions. We'll now see that there are two dimensions driving this part, a diameter of the sketch of the circle and the extrusion thickness. Let's assign a global variable to each of these. For the diameter, I'll double-click this, and I'll type in an equal sign and the letter D for diameter. The glyph pops up that says Create Global Variable. If I now click on this, and then click the green checkbox for OK, we now note in the graphical area that there is a red sigma symbol, indicating that this dimension is being driven by an equation. That equation is very simple. That is that the global parameter D equals 1,000 millimeters. We can do the same for the thickness of the extrusion by double-clicking on this value and typing in equals and giving it a global a name. In this case, we'll call it T for our global variable. Again, a glyph pops up that says Create Global Variable. I'll click on this and click the green checkbox. So now we have two dimensions driven by global variables. We'll only need to vary one for the purposes of this demonstration, that is the thickness. Now let's go ahead and create our static analysis. If your simulation add-in has been successfully loaded, you should see a tab for Simulation. Click on that, and either click on the Study Advisor, or click on the down arrow and select New Study. I'll use the latter option, and first define a static study. You'll see here a variety of options for different other kinds of studies. For example, a thermal study, a frequency study, a buckling study, as well as a design study. You'll note that there is something here called a fatigue study, but we won't be making use of that even in your project that does involve the evaluation of fatigue properties. So do not use a fatigue study for Project 3. For the purposes of this demonstration, let's make a static study and click OK. All of the studies that have been created in SOLIDWORKS will show up as tabs at the bottom of your screen. You'll recall that when we did animation and motion, your motion studies appeared as tabs as well. We'll now have a new tab for our static study. It's titled Static 1. You'll see that there is a study tree with a number of parameters that we can then apply. In the first option here, we see listed the part. If there are multiple parts, then you would find them all listed here as well. For this class, we will not be analyzing or performing simulations on assemblies, only on parts. If you do not see a material assigned here, for example magnesium alloy, then right-click and apply a material at this stage. Next, we see an option for connections. This allows you to define connections between different parts, especially in an assembly. However, since we will only be analyzing simple parts, there is no need to set any connections. The next option is fixtures, or restraints. These are very important. So let's right-click on Fixtures and set what kind of fixtures we wish to define. Again, there is an advisor that can walk you through the different options, and on this drop-down, a number of commonly accessed types of fixtures. We'll be utilizing, both for this demonstration and for Project 3, fixed geometries. When we click on Fixed Geometry, in the example animation, we do see a region here highlighted in green that is fixed. So when the rest of the model is allowed to move, the points highlighted on that face are effectively restrained from motion. If we select a standard fixed geometry, we are then left with highlighting in the graphical area which features we wish to fix. We can fix faces, we can fix edges, and if there were points, we could fix individual points. For the purposes of this demonstration, we will fix the bottom edge such that none of these nodes that will exist once we create our mesh will be allowed to move. For your third project, you'll want to fix the entirety of the face of your beams. There are additional options here that allow you to specify what kind of fixed geometry. For example, by partially only fixing translation in one direction or two directions. However, for both this demonstration and the project, we'll be fixing motion in all three directions, which is the default. I'll then click OK, and we'll note that we have specified our fixtures. The next step in the study tree is to define our external loads. In this case, I'll right-click on this. Again, we can use an advisor or utilize one of the commonly prescribed external loads. For example, forces, torques, pressures, gravity, centrifugal loads, bearing loads, or even temperatures. We'll be utilizing for this demonstration gravity. In other words, the telescope mirror will deform only under its own weight. There will be no external force applied to that mirror. For the purposes of your static analysis and for your buckling analysis for project 3, you'll be applying a force upon a face. For project 3, I suggest you omit gravity, as it's not important. But for this demonstration, I'll utilize gravity as our force, and I'll define the direction of gravity relative to the front plane and ensure that the direction is pointing downwards. And I'll click OK. We now have a fixture defined and a load. Our next step is to create a mesh. You can do this simply by right-clicking on Mesh and clicking Create Mesh. You have an option using the slider to determine how fine your mesh is. For this simple analysis, I'll use a relatively fine mesh. The penalty for a fine mesh is in computation time, although generally it does yield better results. I'll then click OK, and SOLIDWORKS will apply a mesh. We can rotate the model to view this mesh. We've finished setting up our static analysis, so now let's just run the study by clicking on the Run button shown at the top. SOLIDWORKS will take a few moments to solve the equations of motion at every given node, and then show a number of points. There are three different kinds of results that are available to be shown by default for a static analysis. That is the distribution of stresses, shown as von Mises stresses at all points, a distribution of displacement values at all points, and the equivalent strains, which are the normalized displacements at all points. You're free to rotate the model around to see where the maximum stresses and maximum displacements are. We're currently showing the maximum stress values. The color bar here indicates that regions that are denoted by blue have the smallest stress, and regions of green and red have the highest stress. We'll note here that the highest level of stress exists where the constraint lies. This is not an artifact, this is actually a true effect. If we wanted to see the displacements, we can right-click on the displacement result and click on Show. This will now show us the displacement of all the points superposed upon the final exaggerated geometry of the circular disk under its own weight in normal gravity. We'll note here that the deformation scale shown in the upper right indicates that the scale of these deformations or displacements is 413,656 times to 1. So in other words, relative to the total thickness of 300 millimeters, the displacements that you're seeing now have been multiplied by a very large factor in order to be observable. The true values are still shown on the color bar shown at right. The maximum displacement on this model is 2.417 times 10 to the minus 4 millimeters. We can right-click on the displacement and animate to look at how the body deforms under its own weight. This looping animation indicates to us that the maximum displacement occurs in the middle of the unsupported region. In addition, there's some other behaviors at the top of the body which we're not very interested in. Using these animations is a good method to check as to whether or not your restraints and your loads have been applied properly. I'll now click OK. Our next step is to perform a design analysis. We can do this by creating another study, by going to the study advisor, or by directly creating a new study. In this case, we'll be creating a design study. Let's go ahead and click OK. We now have a new tab for a design study. In the design study, we have to set 3 different kinds of parameters. These are variables, to vary, constraints, which must be satisfied, and goals, which are another way of saying find the best solution that satisfies all the constraints. Let's go step by step. First, let's tell SOLIDWORKS what variables to vary and how to vary those variables. On the drop-down that says click here to add variables, we'll note that in this current design study, no variables have been defined. Let's go to Add Parameter and look at the pop-up box. Here we can define parameters to vary in the design study. The default category here is model dimension. If you have properly created your global variables, if you click on the drop-down here, you can select Global Variable. Upon selecting the global variable category, we now have under the References tab to set which global variable we want to vary in the design study. And in this drop-down box, we see all of the global variables that have been assigned for our model. For this design study, we are only going to vary the thickness, T, which has a present value of 300 millimeters. I'll click this and give it a name. You can, in theory, give it a different name, but I tend to prefer to give the name of the parameter in the design study the same name, that is, that the global variable is called, so that I know what it is. I'll then click Apply and click OK. If we now click on the down arrow under Variables, we note that we have a variable, now T. If we select this, we can now tell SOLIDWORKS how we want T to vary. If we hit the drop-down box next to the variable T, we have 3 options: range with step, discrete values, and range. Range with step allows you to define a minimum value, a maximum value, and an increment called a step. So in this case, by default, SOLIDWORKS has decided to select the minimum value of 150 millimeters, a maximum of 450 millimeters, and step increments of 150 millimeters each. This will produce 3 different values, one at 150, one at the current value of 300, and then one at 450. If instead we were to select discrete values, here we would enter in a list of all of the values that we would want it to evaluate. Lastly, we can select range. Range will allow you to go between a minimum and a maximum value, and SOLIDWORKS will automatically pick out a certain number of points to interpolate between those 2 values. I believe by default SOLIDWORKS tends to pick 5 values. You can either use range with step or range. For now, I'll select just range, varying between the default values of 100 for a minimum and let's call 500 for a maximum. Next, we need to define our constraints. We'll note that there are no constraints yet defined, so our option here is to add what's called a sensor. Here is what we define our sensor, which tells us what parameter from our simulation do we need to keep under a certain value. The default sensor type is mass properties, which we will not use for our constraints in this case. Instead, we will select simulation data. Simulation data will refer back to the results of your prior analyses. So by clicking on simulation data, in this case, we have a static analysis defined. In that static analysis, we could grab values of stress, or for the purpose of this demonstration, we'll select displacement. You have to select a component of displacement. In this case, we care about the z direction displacement because that's the direction that we define gravity in. And then lastly, for convenience, I'll select the units of nanometers for that value of that displacement. I'll then also make sure that the maximum model value has been selected. So in summary, we've created a sensor that we'll utilize in our constraint step. The sensor will effectively, upon running this configuration in a static analysis, record the maximum z displacement value in units of nanometers. I'll then click OK, and now define what is our constraint. That displacement value that is taken from the simulation should be, in this case, less than 500 nanometers, referencing the study static 1. Lastly, we now have to set a goal, which is another sensor. In this case, our goal is to minimize mass, and so we could utilize mass properties as our sensor type, and all we have to do is select the part for which the mass should be evaluated. I'll now click OK and make sure that we are trying to minimize the mass. We're now ready to run our design study. In summary, we have these 3 steps. We've defined what variables to vary, what constraints should be satisfied, and what goals we would ultimately optimize towards. Let's go ahead and click Run. Now SOLIDWORKS will create a number of simulation studies depending on the number of variables. Our design study is now run successfully. It's run through a number of iterations. In each iteration, we have a different value for the parameter t. The design study has evaluated whether or not the criterion has been satisfied. If not, it's been highlighted in red. If yes, it's not highlighted. And finally, it records the mass value. In this case, it has described an optimal value of 185 approximately millimeters thickness as an optimal thickness to make sure that the displacement is less than 500 nanometers and that the mass is minimal. Here is where I urge you to take a word of caution. This may or may not be an actual optimal value. SOLIDWORKS sometimes has difficulty interpolating the results of its original set of iterations. This is especially true if the problem happens to be nonlinear in its nature. If your initial range of guesses is far greater than where your optimal value lies, then I would recommend that you rerun your optimization procedure utilizing a smaller range of your values to ensure that you've converged upon the best solution. One telltale sign that failure to optimization has occurred would be that if the optimal value that SOLIDWORKS prescribes to you happens to fall at the very extreme edge of the range of values that you've prescribed. In this case, it has optimized to a single value of 185, which does fall within the range of 100 to 500 millimeters for the thickness. What I'll now do is go back to my variable view and rerun by changing the range for the thickness and decreasing it. Instead of having a range from 100 to 500, let's narrow that down to 150 to 200, spanning the optimized value now of 185. If we now click on Run, we can compare this optimized value to the re-optimized value and see if an improvement can be found. Let's look at our results critically. We now note that our initial value had a maximum displacement of 332 nanometers and a weight of approximately 247 kilograms. Now, when we have a range between 150 and 200, SOLIDWORKS indicates to us that the optimal value is at the extreme value of 150 millimeters exactly. This allows for a displacement that's a little bit larger, but still under our constraint, and is quite a bit lighter, 200 kilograms. It looks like if we want to maximize our performance, we want to maximize the displacement to get just under the constraint of 500 nanometers. Let's rerun this again and decrease our range slightly. Let's run this now from 100 to 150. And again, check our newly optimized values against the values that we've just seen. We note that we still have the same value as before, 150 being determined as the optimal value. This is where you may need to use some judgment. For example, if I were to go to the variable view again, I can now run a range with step value that goes from, in this case, 100 to 150 in a very small step size, perhaps a step size of 5. If I were then to rerun this, we'll now have 11 scenarios that will be run. 13 scenarios that will be run. But this might give us a better chance of being able to come up with an interpolation between two values that do meet our constraints. We can now note from these results that as the thickness increases from 100 to 135, our criterion for the maximum displacement continues to fail, but is edging nearer and nearer to the 500 nanometers that we feel will be our optimal value. Upon crossing to 140 millimeters thickness, we now have an allowable displacement and what would be a minimized mass. We can probably refine this a little bit further by decreasing our range from 135 to 140 in a smaller increment. So if we go back to our variable view, we can go from 135 to 140 in an increment of a half. If we were then to rerun this analysis, we may be able to get our truly optimized thickness value. Again, upon a critical evaluation, we now note that upon the transition between scenario 4 and 5, we've increased the thickness of our circular disc, or our telescope mirror model, from 136.5 millimeters to 137 millimeters. This allows for the maximum displacement to go from just above our criterion of 500 nanometers to just below. Now this value, approximately 183 kilograms, is our true optimized value. For the purposes of Project 3, you will need to simultaneously optimize multiple design variables, depending on the cross-section of the conrod that you're seeking to optimize. This makes it a little bit more difficult to be able to figure out how best to optimize those values. So I will not expect you to go to this much detail into optimizing the values that come out of the study. However, I urge that you do ensure that the values that you're iterating through follow a logical sequence so that you do approach a reasonable value for your optimized cross-sections. Let's briefly summarize what we've just done. First, we created a model. In this model, we properly defined our sketch and then created global variables to drive certain dimensions. We then added the material type in the model. We then created a static analysis and applied our fixtures and our loads. We then meshed the part and ran the study and looked for, in this case, the displacement result. We then created a design study in which we optimized the mass, or minimized the mass, by varying, in this case, the thickness, subject to one constraint. For your project, you will need to not only create your cross-sections appropriately for your conrods, you'll need to run more than one study. You'll need to run a static study and a buckling study that use the same fixtures and loads. You'll then create one design study that simultaneously varies up to 3 of those parameters, subject to 2 constraints, in order to minimize your mass. You'll then do this entire process 4 times, one for each kind of conrod and material combination. Design optimization does not stop at the analysis stage. Engineers should also consider the economic, environmental, social, political, ethical, health and safety, manufacturability, and sustainability impacts of their products. Consumers generally want green products. Sustainable design is a proven strategy for success in the marketplace. Sustainable design is increasingly important in an environment where resources are becoming increasingly scarce. So sustainable engineering is the integration of these considerations, social, environmental, economic, and others, into the product or process of designing a part. All design will eventually be sustainable design. SOLIDWORKS Sustainability is a built-in software package that allows students to environmentally design their parts. This is done by performing what is called a life cycle assessment. Life cycle assessment is a method to quantitatively assess the environmental impact of a product throughout its life cycle, starting from the cradle, where you have raw materials, through its manufacturing and production, distribution, its use, and eventually its disposal at the end of its life, and how and whether it's recycled. There are a number of factors to consider in life cycle assessment. For example, in raw material extraction, if you're using wood, you have to plant, grow, and harvest trees. If you're utilizing metallic products, you need to mine raw ore and then refine it. You often need to drill and pump for oil to make polymers, for example. The next step, once you have these raw feedstocks, is to process the materials into useful form. So oil gets turned into plastic, iron into steel, raw minerals such as bauxite into aluminum. Once these engineering materials have been created, you then have to manufacture your part. There are a number of processes by which you can make a part depending on the material and depending on the actual use of the part. Plastics can be injected molded. Metals can be milled or turned. Almost anything can be cast. Metals, for example, can be plastically deformed in a process called stamping. Your parts then need to be assembled into a finished product and then transported for use. Then it has to have a designed lifetime. How long will the product be useful for? And then finally, once the product is no longer useful, how will it be disposed of? Does it go to a landfill? Can it be recycled? Can it be incinerated? The key elements of life cycle assessment are to identify and quantify the environmental loads involved, how much energy and raw materials are consumed in the making of the part, and in the process, what are the emissions and wastes generated. You then evaluate the potential environmental impacts of these loads and assess the options available for reducing these impacts. The methodology for SOLIDWORKS sustainability can be summarized in the following diagram. We have a number of inputs that go into the process. Those are the material type, the manufacturing process, the region of manufacture, the method of transportation, and how long the part is used. Then, SOLIDWORKS sustainability will determine how much it costs to make the part, whether or not there are similar materials available, and then to evaluate what changes in any of those inputs can result in different values of outputs. Those outputs are summarized in 4 different kinds of environmental impacts. That's carbon footprint, energy consumed, the effects on air and water. And these are summarized both on what's called the dashboard in the SOLIDWORKS interface and in a written report that sustainability can automatically output. So depending on what material you tend to use for a part, you can have a number of different alternative choices. For example, for metals, you'll have options for steel, iron, aluminum alloys, copper alloys, titanium alloys, and others. If you were to select plastics instead, you have a number of plastics for which data exists in the SOLIDWORKS sustainability database. These include ABS plastic, acrylics, nylon, polyethylene, polyvinyl chloride, etc. Once you've selected the material, you'll then have to select a manufacturing process by which to make your part. The available manufacturing processes depend on the kind of material that you select. Aluminum alloys can be, for example, die cast or sand cast, extruded, forged, milled, turned. Plastics can be injected molded or extruded. I urge you, if you're performing the sustainability analysis for this project, to evaluate these different options. Next, you have to select the input manufacturing region. In other words, where is your part going to be made? Each region produces energy by different methods. For example, some regions are heavy on nuclear or hydroelectric power. Others entirely use fossil fuels. This has a large impact on its renewable energy footprint. There are 4 region choices built in to SOLIDWORKS: Asia, Europe, North America, and Japan. You can take a look at all 4 by exploring these options. Next, you have to select the use region. The same 4 regions exist for use. I suggest you keep North America as your use region. However, you can still define how the material is transported from its region of manufacture to its region of use. One of the most powerful features built into sustainability is the ability to find similar materials based on material properties. So, for example, depending on which material properties will drive your selection of materials for a given application, you can find materials within the database of SOLIDWORKS that have similar properties to any of those selected and shown here. This allows you to potentially find alternative materials that might have a lower economic and environmental impact. The environmental impact is summarized by the following parameters: carbon footprint, energy consumed, the degree of air acidification, and water eutrophication. This can be broken down on the dashboard as percentages in each of the stages. the raw material, manufacturing technique, transport and use, and end-of-life considerations. These 4 environmental impact factors will now be summarized briefly. Carbon dioxide and other gases, which result from the burning of fossil fuels, accumulate in the atmosphere, which in turn increases the Earth's average temperature. The carbon footprint is a proxy for the larger impact factor referred to as the global warming potential. Global warming is thought to be responsible for the loss of glaciers, extinction of species, more extreme weather, and other environmental problems. By choosing those parameters, the material type, the method of manufacture and region of manufacture, and the region of use, you can estimate how many equivalent kilograms of carbon dioxide would be emitted into the atmosphere. Total energy consumed is a measure of the non-renewable energy sources associated with the part's life cycle. The impacts include the upstream energy required to obtain and process fuels that are non-renewable, for example, oil or coal, the embedded energy of materials which would be released if burned, so for example, if at the end of life you incinerate the material, there's a certain degree of energy associated with the material that needs to get taken up by the incinerator, and the electricity or fuels that are used during the product's life cycle. By taking into account the efficiencies in energy conversion, we can get an estimate as to whether or not we can decrease the total energy consumed to make a part by making slight modifications to the manufacturing process or the material type. Air acidification is a measure of the degree to which sulfur dioxide and nitrous oxides and other emissions will go into the air that forms acid residues that fall down as acid rain. So for example, sulfur dioxide combines with moisture to form sulfuric acid. Nitrous oxide forms nitric acid. When this acid rain falls back down on the ground, it makes land and water toxic for plants and aquatic life. It also slowly dissolves man-made building materials, such as concrete. So this is measured in equivalents of kilograms equivalent of sulfur dioxide. Water eutrophication is another problem. When an overabundance of nutrients is added to a water ecosystem, for example, phosphates or nitrogen-rich compounds, this can cause an overabundance of, for example, algae to bloom. That ends up depleting the water of oxygen and results in the death of plant and animal life. So, the amount of phosphate equivalents that are ejected into wastewater streams as a result of manufacturing processes can also be quantified utilizing the sustainability module. Finally, sustainability can generate a report in Word document format, and these results can be easily integrated into any kind of reports that you are required to do for your project. You can find sustainability in SOLIDWORKS by going to the Evaluate tab. Looking on the right-hand side, you should see an option for Sustainability. Clicking on Sustainability, after a few moments, SOLIDWORKS will load up the Sustainability module, which is now built into the base form of SOLIDWORKS. Once the Sustainability tab has been opened, you can now scroll through and select the material type, the manufacturing region, specify how long the part will last, the process by which the part will be made, the region of use, the mechanism of transportation, and the end-of-life parameters. Most of these are built-in parameters, and you can utilize the defaults for anything for which you're unfamiliar with. Once you've specified these values, you can assess the environmental impact in the dashboard on the lower side, where you can see, for example, the amount of carbon that's used in the creation of the part in kilograms of CO2 emitted into the atmosphere, the total energy consumed in creation of that part in terms of megajoules, the total amount of sulfur dioxide equivalent emitted into the atmosphere in kilograms, and the total amount of phosphate equivalents emitted into wastewater streams in terms of kilograms of phosphates. If the financial impact factor for that material is defined in the database, down here you will find an indicator as to how much it would cost in US dollars to make that part. For the current part, which is a magnesium alloy, it appears that the financial impact factor has not been defined. I believe you will find that the financial impact factor has indeed been defined for both gray cast iron and titanium alloys. If you do not see the impact factor down here for either of those two alloys, try going up and making a change to the material type and then changing back. There's a little bit of a bug in SOLIDWORKS in the display here because it's trying to indicate the difference in the cost between one material type, called the current value, and the previous value. If you haven't tried to change the material, then the financial impact factor may not show up properly here. Finally, to create your report, simply click on the following button. When you click on this button, Save As, the sustainability output will be generated in terms of a report by default in a Word document format. You can specify the file name and save it to a certain location on your hard drive. You can then open up this report and incorporate those results into your written report for your project.